Hello, my name is Daniel Lima and I'm an aerospace engineering student at the University of Brasilia. In this presentation, I'm going to talk about my current research, the development of 3D printed fuel grain for solid fuel ramjet engine. The current study originates from the missile development for tactical purpose or civil meteorological applications. Figure 1 shows preliminary design of the Air-to-Air missile, and the Figure 2 shows parameters of the solid fuel ramjet motor. The ramjet engine has three main parts: a diffuser, a combustion chamber, and an exhaust nozzle. Among other types, the solid fuel ramjet motor has several advantages: safety of storage, absence of moving parts, and simplicity of operation. However, it also has several disadvantages that complicate its implementation in the aerospace field, such as organizing efficient combustion in a high-velocity airflow and variation on the fuel mass flow rate due to the grain regression. Figure 3 shows the 3D model of the solid fuel ramjet test model developed in the laboratory. The first objective of the research is to create a composite paraffin ABS fuel gram to analyze the engine operating conditions and ensure a constant fuel mass flow rate. And the second objective is to review the geometry of 3D printed grams by bringing out the advantage and disadvantage, which make part of a composite grain design methodology. It grounds on the previous research, where reference publications provide analytical and empirical models on fuel gram design. The methodology was divided into three parts. 1. Study on properties and performance of paraffin and ABS in the combustion of ramjet. 2. Study the equation of combustion parameters as regression rate, relative oxidized mass flow rate, flow and surface areas. And 3. After determining the equations, the software CEA was used to obtain combustion analysis and determine the propulsion characteristics in terms of operation time. 1. Properties of paraffin and ABS. Paraffin is a petroleum derivative. Its properties include purity, excellent gloss, reduced odor. It's also a stable, wide-regressive, ecological green fuel. ABS is a thermoplastic resin derived from petroleum. ABS can melt relatively quickly when subject to specific high temperature conditions. Such a property makes ABS an excellent material for 3D printing. Figure 4 shows the composite solid fuel grain structure used in current research. It has a protective layer of plastic shown by a light gray color on Figure 4. It has thickness proportional to the time of the exposed fire. In such a way, a plastic surface is programmed to sustain a certain amount of time at each specific point, opening the high regressive paraffin shown by a dark gray color on Figure 4, the surface to the fire at a particular time moment. And in Figure 5 shows grain schematics for the mathematical modeling used in this research. 2. Equations of parameters of combustion. Regression rate has several assumptions and allows calculating the fuel melting and combustion in a highly simplified way. Gox is the relative oxidized mass flow rate. A and N are the experimental constants. The total fuel mass flow rate is given by this equation. According to the geometrical definitions in Figure 4, the surface areas AS are equal to these four equations, and the following relations represent the flow areas to the calculate points, these 8 equations. Obtaining the equation system described above and calculating the propellant's mass flow rates, one can proceed to the combustion analysis and determine the ramjet propulsion characteristics in terms of operation time. Results. Figure 6 shows initial parameters for the solid grain calculation, defining the geometry of the grain and flow conditions. The authors calculated the evolution of the grain geometry, full regression, and composition of the combustion products. The motor operation time is 10 seconds. Figure 7 shows the results of the grain regression in graphical forms. And the figure 8 shows the variation of the burn areas in time. As seen from the figure and according to the model, the plastic protection burns slowly and according to the regression rate equation 1, opens the paraffin surface to the hot reacting flow. Same time, the protection layer of plastic resists the thermal loads protecting the hull from overheating. The regression rate of productive material was estimated from 1.25 to 1.49 millimeters per second, and paraffin from 1.14 to 1.38 millimeters per second. The most significant regression of the productive layer happens in the port of the gram, where the cross-sectional area is minimal and the flow velocity is maximal. Such behavior was also observed previously by other authors. As seen from Figure 8, the protective area decreases in time, whereas the paraffin area grows, keeping the total practically constant and close to 12,000 square millimeters. The regression rates and consequently the mass flow rates of plastic and paraffin were calculated by previously present equations. Figure 9 shows the mass flow rates of paraffin, plastic, and their total. Figure 10 presents the distribution of chemical species with considerable concentrations at the exit of the combustion chamber. As expected, the onboard nitrogen has a maximum mass concentration in the mixture is 59%. Due to the fuel-rich combustion, the second component is carbon monoxide is 25%. The concentrations of other species are negligible, at most 6.2%. However, as now they play an essential role in the chain reactions of hydrocarbon fuel. Conclusions. According to the theoretical studies, 3D printing technology allows the fabrication of the fuel gram for a solid fuel ramjet, pre-programmed for a specific regression and mass flow rate profiles. The numerical calculation showed satisfying uniformity of the fuel mass flow rate for 10-second combustion process, which further could be extended by increasing the fuel grain length. The regression rate of productive material was estimated from 0.25 to 0.49 millimeters per second and paraffin from 1.14 to 1.38 millimeters per second. The mass flow rate stabilized during the first 3 seconds from the motor propulsion start and stays nearly constant during operation. Low OF ratio of the mixture to stoichiometric reduced the combustion chamber temperature to 1100 Kelvin and prevents motor overheating and erosion. I want to thank you, Professor Alex, for his support and dedication throughout the research. Thank you for watching and bye-bye.